Hi Year 12, this is Mr. Lim here again, and this is our video on acids and bases and KW. So let's get started. All right, this is what we're going to learn. Okay, all right, so let's start. So water can act as an acid or a base. We've dealt with this before. It can either be a proton acceptor or a donator. Okay, so in pure water, so that's just a whole bunch of water molecules, water can ionize with itself in the following manner, right? Where one of these hydrogens here, this hydrogen here, is transferred across from one to another, and you end up with H3O plus and an OH minus, okay? So it ionizes with itself, which is called self-ionization, all right? And so this one here travels to this one here, making this and leaving this behind, right? So this means that all pure water samples and solutions effectively have a small amount of hydronium and hydroxide ions in them. Okay, so the idea is that these hydronium and hydroxide ions in small amounts are always there. Okay, even in pure water samples. So in pure water samples, okay, for every one hydronium produced, another hydroxide is produced. Okay, so therefore the concentrations of each must be equal, right? So let's go back to here. So the idea is that for every one of these you make, you're going to make one of these. And so therefore, if you have 100 of these, you must have 100 of these if you've only got pure water, right? You have 100 of these, you have 100 of those. You have 1,000 of these, you have 1,000 of those in pure water, which means that the concentration of these two things here must be equal, right? So when they are equal concentrations of hydronium and hydroxide, this is what's considered to be a neutral substance or solution, when the concentrations of hydronium and hydroxides are equal. Okay, now this next point is very important. So when there are unequal concentrations of hydronium and hydroxide ions, the solution is considered acidic or basic. Okay, where the concentration of acidic is where the concentration of H3O plus is greater than OH minus, or if it's basic, the concentration of H3O plus is less than the concentration of OH minus. Now, the idea is that whenever you are asked about something being acidic or being basic, you have to have this idea stated in there. Okay, whenever you're asked to explain something about something being acidic or basic, you have to say, okay, I understand that in the system, there's going to be hydronium and hydroxide ions, and when it's acidic, there's going to be more hydronium ions than there are hydroxide, or when it's basic, there's going to be more hydroniums than hydroxides, okay? And you'll see this a lot in the answer keys. They just state that there's a recognition of an understanding that you are going, in an acidic conditions, you have a greater concentration of one and a lower concentration of the other, and vice versa. You have to include this idea in your explanations, okay? And the idea is that whenever you have this equilibrium system and you keep the temperature the same, if the concentration of one increases, the other one must decrease. Why is that? So let's have a look. So this is the self-ionization equation. Okay. If we were to turn that into a K value, all right, or we call this KW, okay? So it's just going to be H3O plus and OH minus. And if this value here stays constant, then as that one rises, this one must fall, okay? Or if this one falls, this one must rise, okay? So the idea is that they are linked to each other as long as KW stays the same, when like KW will stay the same for any conceptual idea here. So therefore, they are going to, as one goes up, the other one goes down, okay? So when there is an unequal concentration of hydronium and hydroxides, in terms of acids and bases, right? But in a pure water sample, these are going to be equal, and that's our new definition of neutral. Neutral is when equal concentrations of hydronium and hydroxides, okay? So let's have a look here. So when something is added to a pure water sample, okay, when something is added to a pure water sample, it may change the concentrations of one of the two species, but it will ultimately change both concentrations due to the equilibrium system, Okay, so the idea is that even if you change one, you're going to change the other, because if you change one up, the other one's going to go down because of the equilibrium system. So if we have the equilibrium system here, oops, that's not what I wanted, but that's okay. If we have the equilibrium system here, if I add more sodium hydroxide to this equilibrium system, so okay, then the concentration of OH minus goes up. Okay, that means that because the K value, Kw, is equal to concentration of H3O plus and concentration of OH minus. So if this concentration goes up, this one must go down. Okay, and because pH is a measure of the concentration of hydronium ions only, that's these ones here, thus even when a hydroxide is added to the system, the concentration of hydronium ions will change, and therefore the pH will change. Okay, so this is why even though you don't add or remove these via some sort of when you add in the sodium hydroxide, it still changes because you change the concentration of this. Okay, so you change the concentration of this by adding or changing the concentration of this, because there's an equilibrium system that works in there. All right, so that's the idea. The equilibrium system links these two things together. So next, okay, so because this system is an equilibrium system, it can be affected by changes in temperature. And remember, changes in temperature are slightly different to changes in volume and in pressure, right? Because changes in temperature changes the K value of the equation, changes the K value of the equation. So the self-ionization of water is endothermic. Okay, so if we were to write that out, so it would be H2H2O goes to H3O plus AQ plus OH minus AQ, right? So there's a couple of ways to show this. You can show this as a delta H as a positive value, or alternatively, you could show this as a plus heat on this side. So if we imagine what happens if we change the temperature, all right, if we change the temperature, the Kw is going to change. It's going to favor either the forward or the reverse reaction, and you're going to change the amount of reactants and products here. All right, so let's have a look. So if the temperature of pure water changes, the amount of self-ionization will change, and the concentration of products will change. Okay, and really we only care about the products because the products are the only thing that have concentration. The reactants don't. If the concentration of the hydronium ions changes, as because it's one of the products, then the pH will change. So, so if the pH can change, even though there's nothing added to the system, and if nothing is added to the system, then the concentration of hydronium and hydroxide ions will still be equal. This is a key idea, that it's still equal. That means it's still neutral, even if the concentration of hydronium and hydroxide ions is changing, right? So let's go explore that a bit. So let's say that we have a temperature increase, okay? So if we have a temperature increase, what happens to the forward rate of reaction? It will increase. What happens to the reverse rate of reaction? It will increase. Which one will increase more? The endothermic reaction. The endothermic reaction is the forward reaction. So the forward rate of reaction will increase more. Therefore, there's a net forward rate of reaction. If there's a net forward rate of reaction, therefore the concentration of products goes up and the concentration of reactants goes down. Now, there are no reactants here, but it doesn't make a difference. We are dealing with the key idea that the concentration of the products goes up. So when you change the temperature, the concentration of this is going to go up, but so is the concentration of this, because if it's a pure water sample, for every one of the H3O pluses you make, you have to make an OH minus. So this is where they're both going up because it's in a pure water sample. Now, remember that pH is a measure of hydronium ion concentrations. So The pH is a measure of hydronium ion concentration. So when this goes up, the pH will change. The pH will actually go down because it's a negative log scale, but it becomes more of this. But is it becoming acidic? Okay. Is it becoming acidic if there's more of these? Well, remember, acidity has a new definition where this has a higher concentration of this. If this goes up, but this also goes up, these two are still going to be equal. And if they're still going to be equal, it's still going to be neutral. So the pH will no longer be at pH 7, but it will still be neutral. Okay, so that's a key idea, that you can have equal concentrations at a pH not at 7, and it will still be neutral because you've got equal concentrations of those two things. Okay, and we'll practice a little bit of this in class, see how we go. Adios.